Let's start. Welcome back to Koenraad Schalm's lecture series. I'd like to remind the title of Basic Introduction to Holographic Duality and Condensed Matter Physics. This is the fifth lecture of him. Okay, please, Koenraad, go. Let's go.
Thank you, Jung-Yoon. Okay, so the last time we introduced mainly finite temperature version of ADS-CFT, where we saw that at finite temperature, if you also have another scale in the problem, then you have a dimensionless ratio of T divided by that other scale, and you can trigger phase transitions in the system. And the other aspect we discussed that at finite temperature, the universal long wavelength physics and long timescale physics is that of hydrodynamics. And hydrodynamics is parameterized in terms of transport coefficients. And we computed one of these transport coefficients from a Kubo relation in ADS-CFT. And that's when a first connection with real life physics was made, that this viscosity, which was computed, was compared to normal field theories, very, very small. And that actually was also something that was measured through the sound attenuation in heavy ion collisions. So that was the first contact of ADS-CFT with, so to say, applied to the real world. And today we're going to also introduce another scale. We're going to introduce a finite charge density. And the main motivation is that actually condensed matter physics is about systems not just at finite temperature, but also at finite density. And this, with finite density comes a whole slew of new aspects. Now, what meant with finite density, and I specifically say here charge, is that sometimes this is not said with a lot of care. But if you have a finite density, you need some counting parameter to tell you whether the density is 0, 1, 2, 3, 4, 5. In other words, you need a quantum number, and the simplest quantum number is U1 charge. And secretly, when condensed matter physicists talk about finite density, they always talk about finite, sort of a charge density in the system. You have to be a little bit careful, right? Neutrons, for instance, don't have a U1 charge, but you can count with another global quantum number. Right? But there's always a global quantum number involved, which counts the charge. So it means that because there's a global quantum number involved, there's also a global current associated with it. And currents are also conserved quantities, and these therefore also survive in the long wavelength, large, low frequency, infrared, low energy limit of the theory. So at finite temperature and finite density, the theory is not just hydrodynamics, but it's hydrodynamics plus a charge in the system. So it's people sometimes call it magnetohydrodynamics, that has the same formulation, but it's really hydrodynamics plus charge conservation. So those are the two dominant things. Now we know a lot about objects with charge. It's sort of lesson 2 of your quantum field theory, right? We know that if you have a global current, to generate the correlation functions, right, you couple it to an external source, which is a vector potential. And then by taking functional derivatives with respect to that vector potential, you generate the 1-point and the 2-point and the 3-point functions. We focused a lot on 2-point functions in this series, and that will remain the focus. We have shown briefly at the beginning yesterday how to compute 3-point functions, but we continue to focus on 2-point functions. So once you have the 1-point function, the 2-point function, in the presence of a small but finite source, right? The 1-point function and 2-point function are rather trivially related, right? If you just would pull down one more component of the action, one more power of the action, which is proportional to A times J, you get something like this. But I'm now going to use this to again sketch you a derivation of a Kubo relation, right? So for a small but finite source, you see that the 1-point function in the presence of a source is equal to J, the 2-point function times the source plus higher order terms. Now, as I said, the the long wavelength, low energy physics of these systems are determined by hydrodynamics, and now it includes a charge current. And that also means that there are new transport coefficients in this low energy theory. Transport coefficients that are determined by the microscopics, or that parameterize the specific hydrodynamic theory that you have. And in this case, it's a particularly easy one that you all know. The transport coefficient is the conductivity, which is the response, the current, right, that is induced by an external field, in this case, an electric field. Okay. So an external electric field can source a current. So if you take but how do I relate this first expression, where I look at the relation between the 1 and the 2-point function with an external vector field, with this transport coefficient? This is straightforward. If you take the conventional Coulomb gauge, where the time component of the vector field is 0, then the electric field is just the time derivative of the spatial component of the vector potential. In Fourier space, you can invert this relation. That means that the vector field is just EI divided by minus I omega. And so then the conductivity, which is just the functional derivative of the 1-point function with respect to the electric field, and then setting the electric field to 0, is, by this relation between the vector potential and electric field, is nothing but 1 over minus I omega times the functional derivative with respect to the external potential. And then for the 1-point function in the presence of the source, I expanded one more term, and then you get the following relation. Okay, and here you see again an example of a Kubo relation in the same way as we had it before. Here is a transport coefficient. In this particular case, the strict transport coefficient is only the 0 frequency component, but you can of course measure a frequency dependent conductivity. So it's a generalization of a transport coefficient, but the conductivity can be extracted from a 2-point function in the following way. And again, this is the useful way to use it in ADS-CFT, because it only uses the intrinsic low energy information in the system. I do not need a Boltzmann equation. I do not need a microscopic model to compute it. Once I know how to compute the currents, I can extract the conductivity in my system. So we're not going to use it immediately, but this is the general features. At the moment you think of systems in a finite charge density, you should think of also automatically think of the corresponding transport coefficient, which is a conductivity. Okay. Now we're going to apply this to ADS-CFT. And one of the aspects that I didn't highlight a lot yet, but we saw it here and there, is that in order to have a finite charge density in the conformal field theory, as I mentioned, you need to introduce a global conserved current. And the interesting part is that the global charges in the CFT, they must correspond to local symmetries on the ADS side. This is not hard to see. The reason is that in ADS, you have one extra direction. So if you have an object with a vector index, like a current, right, then the obvious generalization to ADS is that this object now has one more index. That's the index in the radial direction. But clearly that object has no counterpart in the conformal field theory, right? And the obvious way in an ADS theory to have a vector-like field of which one component has no physical meaning is to make it a gauge theory. In other words, you make that extra component a gauge artifact. And indeed, if you do the correct counting of the degrees of freedom, you see that a gauge field in one dimension higher has the same degrees of freedom as a current in one dimension lower, a global current, not a gauged current. So this then becomes the prescription in ADS-CFT. If you have a global charge in the CFT, then the corresponding ADS theory must have a gauge field in it and gauge dynamics. And of course, if the global charge is a U1 charge, then you get a U1 gauge field. If it is a non-abelian charge, you get a non-abelian field, etc. Okay. And in a certain way, we have already seen this because the simplest example of a global charge in the CFT is momentum and energy density, right? And that corresponds, as we saw, to the metric field, which is also a gauge field or a gauge prepotential. So we write down the simplest two derivative action in ADS, which includes a gauge field. And that's the following action. Where I've done one thing compared to the previous lectures, I am now going to focus only on ADS4. This has a more an application reason than any other reason, is that many of the deep mysteries in condensed matter physics are related to two-dimensional materials. That is in itself also not a mystery, because if you understand your quantum mechanics, you know that quantum effects are stronger in lower dimensions. So mysterious quantum behavior is stronger in two spatial dimensions than three spatial dimensions. And again, it's stronger in one spatial dimension than in two spatial dimensions. And quantum dots are the most quantum-y animals. So with slightly in the back of our head, this idea that the interesting area to apply this may be two-dimensional condensed matter physics, then when you have a 2 + 1 dimensional CFT, where the extra one dimension is time, and that is dual to an ADS4, where the extra radial direction plays a role. So this is why we're going to focus on ADS4, but all the techniques here apply to other ADS theories as well. It's just that this way I can fix the dimension to a number and it's easier to compute. Now remember, we were interested in objects at finite temperature and finite density, right? And the simplest solution, so I need an object with charge and temperature. Well, temperature we know is a black hole. And it's very easy to extend this black hole to carry some charge. So the simplest static and isotropic, we're thinking about equilibrium, solution is to consider now not pure ADS, but the finite temperature charged ADS black hole, which has the following solution right here, or the metric of that is as follows, where F again is this emblackening function or warp factor, right, which now has two terms, one encoding the mass of the black hole related to the temperature, and Q is the charge of the black hole. Okay, and because this is now a more complicated function, you see r to the 4 and r to the 3, the relation between the horizon radius, where this function is 0 and the mass is not as straightforward anymore, including the charge, it's this more complicated relationship. But so the mathematical expressions become a little bit more tricky, but you can nevertheless compute everything. And the thermodynamics of this black hole is that the temperature is related to the horizon radius as follows. The entropy is related to the horizon radius as follows. And the chemical potential, the object dual to the charge in equilibrium, is just related to the charge by the following relation, where this G here is the effective electrodynamic coupling constant. So this is the system we're going to study. Now there's something that is immediately sort of should strike you. Here I have again copied the line from the previous page and look at the temperature expression. The temperature is depending on the horizon radius, but there's a term 1 minus Q squared over RH to the 4. And this minus sign is incredibly important, because it means that if I choose a specific horizon radius, in other words, a specific mass of my black hole, that is equal to the square root of Q divided by the 4th root of 3, the temperature of this black hole vanishes. However, if you look very carefully at the warp factor here, this object does not vanish. It becomes the following expression. So you still have a black hole. So there is a zero temperature sort of system. It has the period, there's no periodicity of Euclidean time anymore, but there is still a black hole. Okay, so the extremal black hole is something new, right? It is dual to some zero temperature state, but that still has finite density. And that is strange. And that's also, it's a different state than what you start with from in the UV, or it's a different state from pure ADS, right? And so now what really has happened is the following, and I'm going to sketch this from a condensed matter point of view, right? But the aspect is the same here, and we had secretly already seen this when we discussed the Hawking-Page confinement-deconfinement transition when we put the conformal field theory on a sphere. So the conventional story in condensed matter physics is actually very straightforward. It's all non-relativistic electrons coupled to rather heavy atomic nuclei, which are positively charged. And so if I assume that the atomic nuclei are essentially fixed, I just have a very complicated non-relativistic Schrödinger equation for many electrons, right? And if I knew how to solve that exactly, I would be done. I could solve all material problems in the world. In practice, of course, this is impossible, right? So what people do is they make low energy approximations, right? And to focus on the relevant degrees of freedom. And this is encoded in the renormalization group, right? In the fact that at large distances, you can have only the low energy degrees of freedom matter. You can integrate out all other degrees of freedom. And as you do that integration, certain coupling constants change in the theory, right? And this way you can get either directly or through hook and through crook by using the deep insights, especially that Wilson and Kadanoff gave to the renormalization group. You can go from the Schrödinger equation to an ordinary Fermi liquid. That's the standard theory of metals, right? Or an ordinary superconductor, right? Or any other of the somewhat lesser known condensed matter states that you can have. But there are quite a few interesting condensed matter states that we can test in experiment where we don't know how to get it. Okay, and this will be important in a moment, right? So the idea is, and the deeper idea is that at long distances, right, there's also an amount of universality. You don't need to really know all the details of the atomic physics, right? That is really the deep insight of Kadanoff and Wilson. So you don't need to know all the specific details of the Schrödinger equation to get at the effective theory for a superconductor or the effective theory for a Fermi liquid. You just need to know sort of what the general principles are. Now, if that is true, if these details don't matter, right, and these are universal macroscopic physics, indeed, these are known as fixed points of the renormalization group. The fact that for very many different Schrödinger equations, you always emerge in the Fermi liquid. And from very many different Schrödinger equations, if you're cold enough and you're in a metallic state, you end up in a superconductor, right? It means that the details here don't matter. Now, therefore, I can skew the details such that the actual UV theory is a CFT. It shouldn't matter. As long as I follow the right principles, I can still have a Fermi liquid that emerges at large distances from the CFT or a superconductor. And this is very well known. And the only conceit we're going to do here is we're not going to take an arbitrary CFT or a generic Schrödinger equation. We're going to take a rather specific CFT. We're going to take the holographic CFT and try to describe this in ADS theory. Now, even though I start with this very complicated holographically described ADS theory, which is a theory which only should be valid in some large N matrix field theory, once I trigger the renormalization group, right, and I start to look at the emergent universal macroscopic physics, many of these details don't matter anymore. It should not have mattered whether I started with a holographic CFT, an ordinary CFT, or the Schrödinger equation. And one of the main points of the lectures of today is that I will show that objects known as strange metals this way actually do appear from the renormalization group. And for the first time, we actually have a computational theory that can describe strange metallic-like behavior. For the record, 4 or 5 years ago, which is 10 years sort of after this discovery, people have now finally constructed ordinary condensed matter models that can also have strange metals as an emergent state. But holography was, in fact, first. So this is what I'm going to describe now. And this state is going to be this holographic strange metal state. That is actually this very strange finite density, zero temperature black hole. Okay. Now, why? You can immediately see that this state is sort of remarkable and new and was sort of hard to discover with conventional methods. Because the remarkable aspect is not only that I have a zero temperature state at finite density, what also happens is that the entropy at this state remains finite, right? And this violates the third theorem of thermodynamics, right? That the ground state of a system should always have zero entropy. Or the corollary is that if a zero temperature state has finite entropy, then it's ridiculously unstable, unless it is protected by a symmetry, right? Because what does an entropy mean? It means there's a degeneracy of states. It means there are actually very many different states that have the same ground state temperature. And so any small perturbation that will cause a splitting between these states will cause the system to evolve to the actual ground state in the system. So these are normally things that if you encounter them, all alarm bells should start ringing and you're like, oh my goodness, this is maybe not good. But in this particular case, it turns out to be very good. Okay. One thing, if I get time to, in the second lecture today, I will describe some of these instabilities. But for now, let's just study the state on its own and assume that some way or another, it stays in this high entropy ground state and it describes correctly some interesting physics. So that's what we want to do. So let's study this system a little bit better, and let's study it right away in the regime of interest. In other words, low energies, large time scales, right? So how do I study low energies, large time scales? Well, we know this in ADS-CFT. This is mostly captured by the near horizon, the deep interior physics, by the UV-IR correspondence. So let's study the near horizon physics in this charged ADS extremal black hole. So to do that, all the near horizon, all the flow is encoded in this emblackening factor FR. So let's expand this near the horizon, sort of Taylor expanded. We know that at the horizon it's zero. So the first term is just the ordinary Taylor expansion. There should have been a factor of 1/2 here, clearly, right? And we already know from our Gibbons-Hawking trick that the first derivative of F is proportional to temperature. So if we study the zero temperature black hole, that means that the first derivative also happens to be zero. And this is a very well-known fact about extremal black holes. You may remember this from your general relativity class. Extremal black holes have a double zero at the horizon, right? In other words, this warp factor or blackening factor, right, goes to zero as a square and not linearly. So specifically in ADS-4, there's a factor of 6 here times over the units of the horizon radius. Now let's insert this in the metric. Let's now really compute the near horizon metric of the system. And remember that this black hole also had an electric charge, so that there's also an electrostatic potential, which is non-vanishing. And let's also expand that near the horizon. And then you get the following term. Okay, this is just the ordinary applied expansion, and clearly the F, this warp factor F has this double zero. You see it here. The F function also is in the inverse radial components are components of the metric, so that also gets this double zero. And the other parts of the metric are always finite at the horizon. So this just gets evaluated at the horizon. Now let's change coordinates to this value zeta, which is the inverse of R minus RH. And let me define this object L2, which is our ADS radius divided by the square root of 6. Then the metric changes into the following, and the gauge electrostatic potential changes to this. And this is the moment where we all jump up and say, hey, I recognize this part. This is exactly a metric that we've now seen already 7, 8, 9, 10 times. This is an ADS metric in Poincare coordinates, where zeta is 0 is the boundary. And specifically, it is not an ADS, it's an ADS2 metric, right? Because it only has 2 dimensions. So this is this you now recognize as the metric of a space-time with an ADS2 geometry. And then it's a direct product because there's no t or zeta dependence here and no x dependence here of just, in this case, R2 geometry. So the near horizon metric or the near horizon space-time of an extremal black hole is ADS2 cross R2. This, in fact, is a very well-known thing from the heyday of general relativity studies in the 70s and the 80s, that the near horizon geometry of an ordinary Schwarzschild black hole is what's called Rindler space, but the near extremal horizon of an extremal black hole is ADS2 times something. But now we know a little bit more than these physicists in the 70s and the 80s knew, because we know that ADS2 has something to do with a CFT1, thanks to the ADS-CFT duality. There should be some strange scale invariance in this theory, right? There is a scale invariance in this particular case in energy, the RG scale rescaling and time rescaling, right? Or this is actually in condensed matter physics, this is well known that certain objects, certain strange exotic materials show what's known as energy temperature scaling. And this is what's known in condensed matter physics as emergent local quantum criticality. When the response functions or the measurable, the observables of these systems show ET scaling at low energies. We're going to illustrate this even in a more powerful way later. But this is the first ever description of a theory which contains this local quantum criticality in a very concrete quantitative way. And this actually, this ADS2 is the mildest way, sort of the manifest ADS2 is the mildest way to see it. But in a moment, we will actually see that this ET scaling indeed reflects itself in many properties of the system. Mostly this will be in the second lecture of today. So this object, this strange state, right? It's a strange state. And let us now show that it is actually a metallic state. So this is a strange metal state. We don't yet know whether it has to do with the objects that are called strange metals in actual experimental condensed matter physics. So let's call it a holographic strange metal. And we've emphasized at the beginning that we're studying systems at finite density, and a primary characteristic of objects at finite density is that they have a conductivity related to that global charge. So let's compute that conductivity. And we already know how to do that. We have to compute this specific 2-point function. And by now we're all very well versed in how to compute 2-point functions in ADS-CFT. So let's do that. For simplicity, let me use the different Poincare-like coordinates. These are the Poincare-like coordinates, again, where z is 0 is the boundary and not r is infinity. And we just do that because it's computationally, it makes it a little bit easier. Okay, so in these Poincare-like coordinates where the boundary is now at 0 and not infinity, the metric of the extremal ADS4 black hole looks as follows, right? With the warp function here. And you see again the double 0. And I've done one other thing, is I've set the value of the horizon at z is 1. Okay, and that's why there are factors of mu appearing here in the system. Okay, so all right, When you do this, you also need to slightly redefine your ADS Maxwell-Einstein action in that I've rescaled out the electromagnetic constant, and it's useful to scale an ADS radius in front of the vector potential. And this makes a lot of the following mathematics a little bit easier. So like I said, we want to compute the conductivity in this system, which is related to this Kubo relation as follows. And we know exactly now in ADS-CFT how to compute that, right? The 2-point function is related to the normal derivative or the radial derivative of the field divided by the value of the field. And in this particular case, because this is a massless field, there are none of these prefactors. This is exactly the answer to the system. Okay. So we have to solve the ADS-X equation of motion, take its derivative, divide it by the value itself, and take the limit z going to 0. And this is essentially just giving you the subleading part divided by the leading part. And then you have to divide by minus I omega to make it to conductivity. Now we're going to go through this in a little bit more detail because you see another technical subtlety, or there are several technical subtleties that will arise. And as I emphasized in the very first lecture, is that I'm going to try to actually take you through the calculational steps so that you know how to do some of these calculations. So we're going to go through this calculation in a little bit detail. And the reason why I do that is there is a tricky part to the computation. It's not super tricky, but you have to be aware of it. The point is that when you expand to do this, remember, you have to expand in fluctuations around the background to quadratic order and solve the equation of A. But the point is that when you study fluctuations around the background, in principle, you should fluctuate all possible fields, right? Because you can have cross couplings in the system. And that is actually what happens in here. When you expand in all fluctuations of the field, right, there's a cross coupling between the fluctuations in the metric and the fluctuations in the gauge field, okay? And you have to take this cross coupling into account to get the right answer. If you would accidentally forget about this, you get the wrong answer. So let's do that, right? Or let me show you first why these cross couplings appear, right? So remember, we have to expand the action to second order in the variations, and the first order term vanishes because the extremal black hole is a solution. Now, there's an easy way to study the second variation of the action because we are studying gauge fields here and a general relativity. So I secretly already know what the first variation is. The first variation is just the stress energy tensor and the current. So to get the second variation, I just have to vary the stress energy tensor and the current. So let's look at the Maxwell part of the action and look at the Serrant variation. That is just the first variation, as I said, of the stress energy tensor coupled to the variation of the metric times the first variation of the Maxwell equation. Now let's focus on this term. I have to do a variation of the Maxwell tensor because this is already the variation in the field. Okay. Now, before I do that, in this second line, I'm going to look at the variation Maxwell tensor. There's one thing that I can use. I can and I should use all the symmetries that are at my disposal. And the simple thing is that I already know by symmetry that if I think of perturbing AX, right, it can never excite AY because my background is isotropic and homogeneous, right? And so this would violate rotational invariance. The only thing that AX can excite is something else with an X index. Otherwise, the final 2-point function would depend on the direction X, which it shouldn't, right? Because X is just a coordinate that I've chosen. I could have chosen to call it Y, and the answer should be the same. So I can already set all the other ones, in particular AY, I can set to 0. So I'm only going to vary AX. So that means when I vary the Maxwell equation inside FMR and FNS, I only need to vary AX. So let's do this variation. Remember, so this acts on inside here. This is the anti-symmetric derivative, right? And I'm going to carry a lot of stuff around, but you can only focus on this term, right? And let me now write this out and immediately substitute that the index R can only be the index X in the first term. That must mean that this is GXX because the background metric is diagonal. And that must mean that this index X of N should be FNX. The other term in here, which is now mixed around, but that means that the index M should be equal to X. There's a GRS DRX, and then this is now FNS. This is again the black hole. I see that there's a typo here. These other objects don't matter. This should be the black hole in the black hole background. And now what I use is that this FNX in the black hole background, the only component of the Maxwell tensor, because I've now varied the field, so this one I can put to the background value, the only component is the electrostatic potential. And so this N must be the T component. And so you see that this object here can only be the M index can only be the X index, and the N component can only be the T index, because otherwise this object is 0. Okay. And from the second term here, you get the same story, but now this N index can only be the Z index, and the M index can only be the X index in this story. Okay. Right. So this tells you that in this variation of the Maxwell tensor, the only parts that I should worry about is one where the M index is the X index and the N index is either the T or the Z index. Now remember that the Maxwell tensor was contracted with the first variation of the metric. So that means that AX has an off, this is one fluctuation, this is the other fluctuation. So AX mixes with the two specific metric fluctuations, HXT and HXD. And this is what the point that I wanted to emphasize. You have this cross coupling in the system. Now, once you know this, you just have to be careful and work your way through it. Right? So remember, I've only did the second variation of the Maxwell term, but there's also the Einstein-Hilbert term in the action, right? And here we're going to use another trick, which is, again, of two components. Again, I need one of these indices of H to be X, because otherwise I already know from the symmetries that the answer will be 0. And now the trick is that if I take an off-diagonal metric fluctuation, so I take M not equal to X, right? But if this field itself does not depend on the X direction, and I don't need to, because the term that I excite only depends on the Z and the T direction, then this part of the Einstein-Hilbert action behaves exactly as an electromagnetic action, because it behaves essentially like a vector in the orthogonal space, and it's a gauge field, and the universal gauge invariant action for that is the Maxwell action. And the only thing you have to realize is that it has an effective space-time dependent coupling in the system. And this is a very well-known trick in general relativity. So I can immediately use that trick, and instead of having to do all this work of expanding the Ricci scalar, et cetera, I can immediately write down that the fluctuations of HXM are just encoded in an effective vector field with an effective field strength little f. Okay. All right. And now I put everything together. Okay. In fact, for 0, now again I use the symmetries, right? This effective vector potential has 3 indices, because I only should worry about the off-diagonal components. So AX was already by assumption 0, right? And again, AI has to be 0 because that's incompatible with the symmetries. So I only have to worry about AZ and AT. And if I have 0 momentum, in other words, then the only non-zero component of this field strength is FZT. Okay. And now it becomes easy. Now I can write down the full second variation of the action. The first term here is just that effective Maxwell action for the variation HX capital M, where capital M is not X. It's just dz times this effective vector potential AT. I Fourier transformed here, and then there's the cross term between the two. And then here are these 2 terms that we just computed. These cross couplings between the fluctuation AX and the fluctuation now characterized as AT. And in fact, if you did that correctly, there are 2 terms. This comes from essentially the HMN coupled to the variation of the stress energy tensor. And then there's the fluctuations of the Maxwell term itself, the F mu nu term. So these are the 6 terms. Okay. Now, so I actually have 3 fluctuations that cross couple. I have delta AX as a fluctuation, I have AZ as a fluctuation, and I have AT that's a fluctuation. However, the interesting part is that you should notice that AZ as a function of Z, right, has no derivative terms, right? So AZ, if I look at this equation motion, it's algebraic, right? It just says AZ is something. And what you know is that if you have an algebraic equation of motion, I can just substitute it back, just solve it directly. I can substitute it back into the action. So I can solve for AZ and substitute it back in the action, and then I get the following terms. This actually reduces rather simple. Here I have still the two cross terms. There are some changes of coefficients from adding these 2 terms, and this is still the Maxwell action itself. And if you study this system a little bit more, you realize that if I integrate in this term, if I integrate the dz by parts, right? And also here, integrate the dz by parts, you can use on phi prime the effective equation of motion, right? Which is just the Maxwell equation in the background. And then you find a decoupled system. You find that this combination squared is on its own, which has an AT, right? And then there's a term with only delta AX. And now we're done. Now we have taken into account this cross coupling between the 2 systems, and I've actually diagonalized it in 2 independent fluctuations. For the conductivity, we're only interested in the fluctuation dAx, and now I can find its equation of motion. This then is the equation of motion for delta AX. And now we are in the position to do what we do always. Now we can just solve this equation of motion, right? Extract the derivative and the value at the boundary and take the ratio to get the conductivity. The one thing is, of course, is that this is actually once you substitute in the background field values for G, T, and F, it becomes the following equation. And in particular, you see here the full warp function F. And this is therefore quite a tricky equation to solve, right? And rather than solving it analytically, what people resort to is solving it numerically, right? The systems now become so complicated that there are no simple, basically symmetry constrained functions that solve these systems, right? So let's solve this system numerically and extract the conductivity from this ratio. You can do that. This is not so hard. It's a single differential equation. You can use Mathematica. You can use discretization and Python. There are many different ways to solve this numerically. And what you get out is the following. Note, by the way, that this object in general can have, because I have an omega, both has a real part and an imaginary part. So here I've plotted the real part of the frequency, and here I've plotted the imaginary part of the frequency. And what I am showing here is the result as I increase the chemical potential in functions as a function of the temperature in the system, right? And so I saw for small chemical potential, there's a small change, and as I increase the chemical potential, right, what happens is that this object here, there is this gap that fills in that decreases. Now, one thing I have not yet mentioned is that the real part of the conductivity, right, actually obeys an optical theorem, right? In other words, that if you integrate the area under the curve here, that this should not change. This is a constant, right? This is essentially related to unitarity, or what you know as the optical theorem, right? That the imaginary part of the forward scattering cross-section of the forward scattering amplitude is equal to the total cross-section. So that means that the fact that it looks like here that the integral under the curve shrinks, but that's not true. Actually, what happens is there is a small delta function peak here that is growing, right? And that's absorbing all the weight. And the reason you can see this delta function peak is that's why you plot the imaginary part of the conductivity. A delta function peak here corresponds by the Kramers-Kronig relations to an pole in the imaginary at 0 in the imaginary part of the conductivity. And you can fit precisely to this term a function that goes as 1 over omega. And as you see that pole that becomes stronger and stronger as you lower the conductivity. Okay. Now, what does that mean? This is the real part of the conductivity. This is the physical conductivity. What does it mean that I have a delta function here? That means that if I look at the DC conductivity at the 0 frequency conductivity, the value of the delta function is infinite. And this is in fact a very well-known aspect or a very well-known problem that plagues finite density systems. Because if I have a system at finite density that is charged, and I put in a small electric field, the whole system is going to want to move. And if there's nothing that stops it, it's going to want to actually accelerate moving, and it's going to accelerate and move forever. And that results literally in an infinite conductivity. The amount of charge that you're transport per second is infinite. So in real life condensed matter systems, there always has to be some mechanism that breaks or that causes friction on this movement. Otherwise, you have a delta function in the DC conductivity. This is an aspect I will not address later, but I just want to explain to you that the general features of these results reflect exactly what you expect based on your simple condensed matter wisdom. So this was a part 1. Are there any questions about this?
So can you justify the title of this, I mean, the conductivity of a holographic strange metal? Okay,
so this is the conductivity. That's easy, right? And the strange metal, I've now shown you that this object has a finite, in fact, it has an infinite DC conductivity. That's the definition of a metal, right? So this is the conductivity of a metal. We've conducted a holographic computation, and the only thing that I have not really emphasized or argued super convincingly yet is that this is a strange metal, except for the fact that this is some object which has an ADS2 near horizon and therefore has a 0 temperature ground state entropy. And that's at this moment the only strange part. But in the next part, I will try to clarify more why this is strange. So
okay. So it's so far it's not
So at this moment, the only strangeness is sort of the fact that there's this ADS2 on the horizon, but actually the conductivity itself, you cannot see that it's strange. That is correct. If that's your point, in the conductivity itself, you cannot see that it's strange.
I also have a question.
Yes.
So is there any comment about the small temperature limit of this figure? I mean, because before you talk about some geometry for the t goes to 0 limit.
Yes.
And I mean, so I'm just curious about, are there any interesting connection between that geometry and this conductivity behavior in small temperature limit?
No, you have to be a little bit careful here. How do I want to say it? You should replot these objects as omega over mu rather than omega over t to get to understand the zero temperature limit. But in the zero temperature limit of the system, what you get is basically that's you get a very, that's like making mu extremely large, right? Mu is measured in them, and what you get is actually this delta function becomes almost separated from the system with a step function gap, right? But that is also, it's very easy to understand this from standard condensed matter physics. There are some interesting aspects which I will not discuss in these lectures, unfortunately, because I don't have time. Is once you go to more exotic holographic strange metals which don't have an ADS2 horizon but the so-called Lifshitz horizon, and then you can have interesting zero temperature behavior of the conductivity.
Oh, thank you.
Good. Any further questions?
Yeah, I have a question. Sorry.
Yes.
It's related with the first part of the lecture. When you introduce the temperature of the black hole, there's this term that was proportional to the charge of the black hole. Like, and there you can get the zero temperature limit. I was wondering if you have a black hole with a huge charge, like maybe you can get negative temperatures. Is that possible, or does it have a physical interpretation? Like condensed matter, normally you have the inversion population temperature, like say it's negative, but it has this.
No, you cannot get negative temperature. I mean, it's a bit related to the parameterization of how I
like for your answer, you won't be able to get that kind of results.
No.
Oh.
The way you have to understand it is actually in an extremely. I should have not written q squared over RH to the fourth. If I put the RH here, it's easier to understand what's happening. Is that the fact that that you put charge in the system, that charge itself carries an energy density with it.
Okay.
Right. And so it's not like you have separately an energy reservoir and a charge reservoir and you can take it away. The physics of it is that once you put in charge, you automatically put in some energy. You can put in some extra energy that gives you a temperature, but you can never put in, right? You can never put in any lower energy.
Oh.
Okay. And this formulation, this mathematical formulation writes it a little bit strangely, but you should really write it as there's a minimum, right? And with a plus, if you understand what I mean.
Okay. Thank you.
Okay. If there are no further questions, we still have some time, and maybe I start with the next part already, and then we take a break there halfway through. Is that a good idea?
Yeah, all right.
Yes? Okay, so now I'm going to try to answer the question that was already raised by several of you, including Sangjin. I'm going to try to illustrate a little bit more why this really is a strange metal. Okay, and this has to do with the fact that when you study these systems with a fermionic probe, you really find what are called non-Fermi liquids. And a non-Fermi liquid in condensed matter language is just another word for a strange metal. So if I can show that this is a non-Fermi liquid, I have shown that this is a strange metal. So to do this, lots of condensed matter physics is related to electrons. Electrons are fermions, so everything is about spin 1/2 physics or fermionic physics. And so what we have to do next is we have to study system, an ADS CFT system, where I include objects that are spin 1/2 or fermions. And there's a very natural way to do that. Once I know ADS CFT, quantum numbers must be quantum numbers. So I have to use a spin 1/2 field in ADS, and a spin 1/2 field must be anti-commuting. It must be a fermion. So I can just couple a Dirac action to my Einstein-Maxwell action. Right? So the system I want to study is Einstein-Maxwell-Dirac. And it looks as follows. And there's several subtleties here that let me emphasize them one by one. All these subtleties are related to the fact that I'm studying fermions in a curved space-time. And the subtlety is related to the fact that spin 1/2 is a representation under the Lorentz group, right? Which seems to be a property of Minkowski space-time. Whereas, of course, once you have a curved space-time, the global space-time generically will not have Lorentz symmetry. So the way that's resolved is that you think about spinors or fermionic fields as having representation under a local Lorentz group, right? There's a local frame, which is just by eta IB. And then you can pull this local frame to the space-time metric with an object called the Vielbein. And this Vielbein is dependent on the local coordinates in the system. And that is this little object here. And with this Vielbein, you have to find a way how to transport your local frame from one point to the other point. And that is done with what's called the spin connection. And the spin connection is essentially defined by the fact that you want the Vielbein to be covariantly constant. And that relates the Christoffel symbol to the spin connection. This is just one way, and there are other ways to do it, but this is the standard way to transport the local frame from one point to the other point. And this allows you to define a Dirac action in a curved space-time with very ordinary Dirac matrices gamma AB, which are just constant objects that anti-commute to 2 eta AB. So these are these various coordinates. And then the one thing we add to it is that just like an electron, we want that this fermion is charged under the gauge field, right? Or carries a U1 charge, so that when I add finite density to the system, I can also include a finite density of these fermions. So this is the action that I have, and I now want to study this. And the object that I want to study is, we stay with our familiar territory. I want to study the two-point function of these fermions in this now charged black hole background. And I want to see what I get out. Okay. Now to do that, there are several technical issues, and let me walk you through them one to one. The biggest technical issue is that, as you know, the spinner has dimensions, is an object with various components whose number of components depends on the number of dimensions in which you're in. So in dimension d is 2n, and d is 2n, and spinner has 2n components. That means if you have an even dimensional bulk, say ADS4, with d is 2 to the n, then the spinner actually has double the number of components to the n than you would naively expect based on the dimensionality of the boundary. Okay, so this sounds weird. Okay, now I have a problem. It sounds like a worse problem than I had for the gauge field, where I just had one component more because I had one radial index, but here I have double the number of components. Okay, actually also here, the resolution is not very difficult. The resolution is the fact that the action for a fermion, right, is not second order in derivatives, but is first order in derivatives. Okay, so this is like more like a Hamiltonian system where I have P and Q dot, rather than a Lagrangian system where I have a Q dot squared, right? And in fact, that this is precisely what's true. And if you may have learned this in your quantum field theory course, that the Dirac action is indeed a first order action, which simultaneously describes the actual fluctuation and its conjugate momentum, right? But these, of course, are not independent degrees of freedom, right? The independent degree of freedom is the fluctuation, and its conjugate momentum is related. So we need to some way or another identify within these two end components the fluctuation. And essentially, you're a bit free how to do that. And a very straightforward way is to use the fact that I secretly have this extra direction. So I also have a gamma matrix in this extra direction, right? And I can simply project on eigenstates with respect to this gamma matrix. That is a nice, clear way, because I had this extra gamma matrix anyway compared to the story. This is very much inspired by, if you remember, chiral fermions, right? That you can project by gamma 5 to get left-handed and right-handed formulas. And 5 is precisely 1 dimension higher than the 4 dimensions you have in space-time. So let's do that. We simply project on one object psi plus, and then the other one we call by definition the conjugate momentum. And if you do such projection, then the Dirac action actually splits in 4 terms. There are the kinetic terms, which you know are diagonal in this projection, and there are mass terms, which are off diagonal in this projection. Now, there's a second technical issue that appears when you study spinors in ADS-CFT. If you have scalars, we saw that the boundary term appeared naturally. It appeared because we had to integrate the action by parts, and then there was a normal derivative term that was left on the boundary. Now again, here, the Dirac action is first order. I don't have to integrate by parts. So it doesn't appear in the same way. Okay. However, it appears precisely due to that aspect that I discussed a moment ago. The fact is that the boundary value, right, of psi minus, which is the conjugate momentum now, right? That's not independent, but it's related to the source by the Dirac equation, right? And because this is not independent, one should do a variational approach. You should only vary independent objects. You should not vary objects that are dependent on each other. So we have to some way or another make sure that the boundary value of psi is not varied on the boundary in the right way. And you can do that by adding a boundary term, which is the following, okay? This way, then you can ensure that the variational problem for psi minus or for the whole Dirac action is now well defined. Because if I add this term and I vary psi minus in the system, holding psi plus fixed, remember, because we're studying a Dirichlet problem, so you want to keep psi plus on the boundary fixed, but you are allowed to vary psi minus, right? But this term shouldn't be there because the boundary value of psi minus is related to the source in the Dirac equation. And so I should not be allowed to vary it. It's already determined by psi plus. And this is precisely now determined that if I vary the Dirac equation, right, then you see, because you have, when you vary it, you have to vary both the conjugate term and the term inside the momentum. So you integrate by parts, but that integrate by parts gives you a psi minus variation on the boundary. And this one, I don't know how to determine because it's determined in terms of psi plus. Here, I can just put this to 0 because I hold the psi plus fixed. But this is now precisely designed such that this term cancels. And now I have a well-defined variational problem in the system. This is actually a very standard trick in many of these systems, there are certain boundary terms that are related to the extrinsic curvature of the boundary that you can also understand this way. There are often other ways to understand it as well, but this is one clear way to understand how such a boundary term may arise. And as we know from ADS-CFT, the essence of this boundary term is crucial, because this is where all the dynamics comes from. Because once we evaluate the action on shell, right, it's the boundary term that gives everything. And of course, for a Dirac field, that's even more obvious, because as you know, the Dirac action is directly proportional to the equations of motion. So on shell, this bulk term vanishes, and everything comes from the boundary term in the same way as for the scaling.
Sorry, Koenraad.
Yes.
So I think I lost some point somewhere, but so is it enough to adding this boundary term only for the horizon? I mean, so
So this should be not at the horizon. That's a typo. This should be at the regulated boundary. My apologies. I will correct that in the notes. Good observation.
May I ask a question?
Sure.
So if you left fermions out and you had only bosonic quantities, would it still be possible to argue that one has a strange metal, or that there's something strange about it? Because as soon as you said that so far you hadn't demonstrated anything particularly strange, and then you began a trajectory towards showing that it is strange, and to get there, you immediately introduced fermions.
The answer is both yes and no. Let me first give you the answer why it's no, because for many condensed matter physicists, a strange metal is defined by the fermionic response function.
Yeah,
So
that's right.
That's sort of a definition thing. However, the answer is also yes, because I will discuss it at the end of this section. The specific features that allow me to deduce that the fermionic responses are of the same strange metal, you would also see in bosonic fluctuations. And this is related to the way the self-energy term in these systems appears. But this self-energy term appears mathematically in the same way in bosonic fluctuations. So indeed, you would also in bosonic response functions find these anomalous self-energies. And that in a certain way could allow you to say that I don't need to study fermionic response functions, but I can study bosonic response functions and already think I have a strange metal.
So the peculiarities
in that sense,
not
the answer is
just,
both yes or no.
They're not just because of the fermions. There's something very peculiar to start with.
No, and it's precisely related to this ADS2 feature. And that's why I emphasize it in the first part of this lecture. And you will see as we go along why this feature is specifically tied to ADS2 and it's not tied to the fermions.
Okay, thank you very much.
Okay, so there's actually a third technical issue. Okay, and that's the fact that this fermionic, but this technical issue is extremely familiar to you from quantum field theory. Right? This is that the fermionic correlation function is not a function, but it's really a matrix between spin components. Right? You can it's the response if you turn on one spin component in the fermion, how all the other spin components answer. Right? And the way you do this in quantum field theory is rather than studying the full matrix in all generality, which you can also do, but it's complicated, is you try to separate out each independent spin component separately. And you can do this by helicity projections, for instance. Okay. One way to do that is actually we do as follows. Let me first quickly undo the projection under gamma r. So let me write down the full all spin component Dirac matrix. And then there's a technical trick, which is very well known in general relativity, that if you have a metric and therefore whose vielbein and whose spin connection only depend on a single coordinate, right? So many black holes have this, where everything depends only on a radial coordinate, right? Then, only then, if you redefine your Dirac fields in the following interesting way, where this is the determinant of the metric, minus g, and this is the inverse metric g in that one direction where it depends on, then you can show that this precisely removes the spin connection from the problem, right? So for this field psi, you just have a much simpler action, which is as follows. And that's, of course, a great use, because a lot of the mixing of the spin components sits in this Lorentz connection, gamma AB. Okay. And so we are actually interested in such background configurations. So E depends only on R, and on top of it, A is only A0 is 0. It's electrostatic potential, also depends only on R. So this is now a homogeneous differential equation where I only have this gamma here and this M here. Okay. And this is now very analogous to studying spinors in flat space-time rather than curved space-time. So some of the mixing between spin components due to curved space-time is removed thanks to this peculiar feature that I'm studying it in a background which only has one coordinate dependence. Okay, so the way you would do that in flat space-time is you Fourier transform and you can project it onto two-component spin eigenstates. Okay, and here a similar projection exists, right? But it's on transverse helicities. If you study it deeply, it's the spin is always orthogonal to both the direction of the momentum and the radial direction, right? Now, I'm going to take you through some steps here. I understand that this, especially because they're rather technical, will be hard to follow, but let's try to do it anyway, right? So the way you do it is just like in quantum field theory, choose a very specific basis for your 3+1 dimensional Dirac matrices. This is the basis that we choose, right? And we choose the boundary, we choose one specific momentum. That is the key feature also in quantum field theory. We don't choose an arbitrary momentum, but we choose the momentum to be in the x direction only. Okay? And we can freely do that, right? We can just call any direction x, or we can rotate to a basis where the momentum is only in the x direction. Okay? And this projection onto eigenstates is now related to the fact that once you choose the momentum in a single direction, right, there is a combination of gamma matrices which commutes with the Dirac operator, right? And the reason is, of course, that one of the derivatives of the Dirac operator then is 0, because there is no momentum associated with it. And so often it's that component that computes with the Dirac operator. The tricky part in ADS is that it's not gamma y, but it's gamma y times gamma 5, which commutes with the Dirac operator. And so if I wanted to study the Dirac equation of motions, but there's which is essentially a 4x4 operator, but I have a matrix which commutes with it, I can simultaneously diagonalize the two, right? And I can project onto eigenvalues of this basis. And therefore, I can project onto the eigenstates of gamma 5 times gamma y. And that reduces the 4x4 problem to two independent 2x2 problems, okay? Which, moreover, they're actually related in this case by a helicity flip, which sends kx to minus kx. But I can therefore completely focus on one 2x2 system rather than a single 4x4 system. And that, of course, is much easier. Oh, okay. So if I do that, this is the equation that I get, where these sigma are now the Pauli matrices here. And I've used a rather funny notation where secretly I've used the fact that the metric in the black hole is diagonal, and the field line is therefore nothing more than the square root of this metric. So this is the system that I now have to study, but I do still have a 2x2 system in this system. Okay. More than this, I cannot do, and this is related, of course, to the fact that I have a first-order equation, which simultaneously shows you how the fluctuation and its conjugate momenta evolves, right? So, but now let's try in this first-order system. Nevertheless, we apply the CFT ADS CFT wisdom and see what we can extract. So we need to construct the CFT correlation function. We know that the essential part is the behavior of the solution near the ADS boundary, right? And near the ADS boundary, the metric is just that of ADS, right? So these field binds just behave very similar as if you're in pure ADS. They're just R over L in the radial direction or L over R in all the other directions. So near the boundary to leading order in R infinity, this whole equation actually reduces to this following very, very simple equation. Okay, right? Now sigma 3 has an eigenvalue +1, right? And it's diagonal in +1 in the upper index and -1 in the lower index. And so you very easily see that this has two independent solutions. In the lower index component goes as R to the ML, and the upper index component goes as R to the -ML. Okay. And here you see already a little bit the aspect that I discussed several, or that I mentioned several times, but here you see it physically represented, right? There's a leading component because this is in coordinates where R infinity is the boundary. So this is the divergent part. So I should think of A as the source. In other words, the lower component of chi1, right, is the source field. But remember, if the lower component of this is the source field, I'm working in this first order formalism. The other component must be its conjugate momentum. And the conjugate momentum is the conjugate momentum in the radial direction. So that should play the role of the derivative of the field that you use in the scalar. And indeed, you see that the response sits in the conjugate field B and is subleading and is completely finite as I take R to infinity. So you can already immediately guess what the Green's function, what the two-point correlation function for a fermionic field in holography is. It's roughly something like B over A. And I can show that in a little bit more detail. Given the time that that is, let me see if I can do that. But once I have that, I will stop and I will leave the analysis for after the break. Okay. So let me say one thing is that this is just a more technical thing is that remember this is a first order formalism. But as you know from fermions, you can by acting with an appropriate extra derivative, you can make it a second order formalism, which is now diagonal. It acts on each component independently, right? And you can compute now the two independent solutions to this system in terms of the second order equation of motion. And once you have that, you can actually these homogeneous solutions to the Dirac equation, right? These second order solutions are also solutions to the Dirac equation by construction. You can construct the explicit Green's function for chi1. Now, remember, chi1 is a 2x2 matrix. So here you take the outer product, right? This gives you a 2x2 matrix in these solutions. Where again, you use the same, I'm using the same notation here as I used for the scalar field. Psi b is specifically a solution where near the boundary, its component A is 0, and psi int is a solution whose boundary conditions are set by the interior, right? So if you assume that all of these obey the Dirac equation, this gives you the Green's function in the solution here. Phi b is the normalizable solution with leading coefficient A0, and phi a interior is determined by the appropriate boundary conditions in the interior. One second. Okay. Now remember, I had to do one thing, right? Now I can substitute this into the boundary term. I don't have to worry too much about derivatives because the boundary terms had no derivatives, but I did have to do one thing. Remember, this boundary term was a projection on psi plus with respect to radial direction and psi minus. And in this case, this reduction corresponds in terms of this reduced basis where you have commuted with gamma 5, gamma y to 1/2 minus sigma 3, right? And so that means that psi minus is determined in terms of psi plus by the following relation, okay? And now I can substitute all this into the boundary reaction, right? I substitute psi minus is this relation to psi plus. And here you get the answer in the system. This is this projection operator here. This is the Green's function. And these are the values psi plus at the boundary. All right. Now, and do the last step. I need remember that near the boundary, the interior solution has both a B and an A component, and psi B only has a B component. And if you substitute all that in the boundary action, this reduces to this simple form. All that complicated machinery reduces to this. And there's one final technical issue that I want to say is that the difference between fermions and bosons is that the fermions are naturally complex fields. And here you see that this doesn't reduce to a nicely B over A. But if you do this for the first time in zero density pure ADS, you notice very quickly that B and A int can be chosen real. And this therefore, this reduces to the usual B over A that you could have immediately, or that would have been your natural guess based on the first section, right? And this gives you then the Green's function with fermions, just B over A. Yeah, for the single spin component. And you may say, okay, what happens in other situations to ADS? You have to be a little bit more careful. It's related to the properties of the interior boundary condition and various other aspects. But you can actually prove that this B over A formula, despite this, is actually true for all other asymptotically ADS backgrounds as well. Right? So now we're back to the usual story. Also for fermions, I have to solve the Dirac equation. I first project on gamma 5, gamma y. I pick a specific spin direction. And then I look at the leading and the subleading component. And I take the ratio. And then I have the Green's function. And given the time, I propose that if there's still questions, please ask questions. But I'm going to actually do this for the black hole after the break. Are there any questions?
Is A and B are just a number, or
A and B are now just numbers, yes. Because I had a 4-component spinner, right? And I now project this 4-component spinner on eigenstates of gamma 5, gamma y. So there's a 1 eigenstate, which is now a 2-component object, and there's a 2 eigenstate, which is also a 2-component object. And I only focus because they're now independent. The Dirac matrix, the Dirac operator becomes block diagonal in 2x2 matrices. I only focus on chi1 sector, right? But chi1 is still an object which has 2 components. But if I look at the asymptotic behavior of chi1, it has 2 components. This A is just a number multiplying the vector 0, 1, and B is just a number multiplying 1, 0. So A and B are now indeed just numbers. Okay, and this therefore is not the Green's function of the most general sort of covariant Green's function, which is the Green's function of all spin components at the same time. It is the fermionic Green's function of a single spin component. And that's why it can be a number.
do you know how to actually define or discuss the spin itself in terms of this?
Yeah, so if you do this in the covariant notation, which particularly is the one that we used here in Leiden when we did this for the first time, it becomes mathematically quite complicated. But then you can discuss all these aspects by simply because then I have the covariant Green. I have the full Green's function matrix between all components of the fermions. And if you want to study spin responses, you just multiply it by the appropriate gamma matrices to project on a spin.
Are you going to write down that? I mean, for example, can we discuss the, for example, magnetization in terms of the spinners?
In principle, yes. I don't think anybody has done that.
Right. So,
but in principle, yes.
I was very curious.
Well, actually, what people have done, including myself, is studied how these fermion correlation functions change in the presence of a magnetic field. So not really how the magnetization is affected when you have spin in the game, but the simpler answer is how does an external magnetic field act on the spin response, on the fermionic response, which especially, of course, if you have a finite density system with a Fermi surface becomes very interesting because you get Landau levels in the system.
Right. So it's not really properly done, you say.
Well, the sort of the fermionic contribution to the magnetization of a system, I don't think has been done, no. But this is hard because, but in principle, it should be doable. It's if you just want the magnetization that's also just given by the static component of this 2-point function. Yes. It's a good point.
Does that mean that magnetized systems have, spontaneously magnetized systems haven't been studied yet?
No, and so spontaneously magnetized systems have absolutely been studied because you can have, oddly enough, even though we don't have magnetic monopoles in the real world, you can have magnetic monopole black holes, right? And or magnetically charged black holes, and these have been used to study spontaneous magnetization and or induced magnetization.
So it's a matter of how you factor how you bring the magnetization into the problem. You said if you're trying to do it without the black hole, just with the fermions, that's not been done yet. But if you do it via the black hole, then you can do that relatively easily.
But I think the question that Sang-Jin was referring to is let's say you have already a magnetically charged black hole, and now you put fermions in that system. Now you can study simply the fermionic response. That is straightforward, but you can also ask the question at higher order in perturbation theory. Do you get an enhanced magnetization by the fact that sort of the black hole interacts with these fermions, sort of in the normal way you think of if you have a piece of metal and you put a small magnet to it, it will magnetize the metal and you get a stronger magnet. Right, and that effect has not been studied. And you can even ask the question: if I study it in a non-magnetic black hole, can sort of the spin interaction of the fermions themselves have spontaneous magnetization? That's also not been studied. That would be a 4-point function in the fermions to study instability. Those are hard.
Okay. Yeah. There's two things I was curious about in the experiment. It's possible to tune something, say from the superconducting phase into a strange metal, and then to another phase, maybe an insulator, and see how that goes with temperature, or, and actually do it all in one experiment. So I'm wondering if say the strange metal phase is frozen into how your black hole is set up, are you able to study continuously how you go from one phase to another? And then another question was, you said earlier that these strange metals were the first realization. The ADS-CFT strange metals were the first real mathematical realization of it, and more recently, say in the last 5 or 6 years, there's been something else. I think you were referring to the SYK model.
Yes, precisely.
And I'm wondering if you'll have any further comments about the relationship between this and the SYK model, or the relative strengths and weaknesses. later?
No, I would happy to do that. In fact, was it 2 summers ago, I lectured at APCTP precisely about this relation. But the request to me for this school was not to do that, so I have not. I'm sorry.
I imagine it's could go on quite some time about it.
Yeah, that's a whole independent series of lectures by itself.
It's too much. Okay. But then there's the other question. Can you tune from one phase into another and see how that
Yes,
goes?
absolutely. Yeah, in fact, we will do that. If I get a chance to it, I will do a tiny bit in the next hour.
Okay, thank you, Koenraad.
You're welcome.